Okay, I'm Brian Motil. I'm the chief of the Fluid Physics and Transport branch up at Glenn Research Center in Cleveland. And before I get started, I just want to make one comment to the first question that the gentleman asked about whether you can orientate your hardware to minimize effects of gravity. I don't think we necessarily do that on station, but what you can do, and we do this in fluid physics and a lot of our experiments, is we request that we operate during quiescent time periods. So that's how we get around that. We actually know when they're going to do something which would create a disturbance in a direction or a frequency that's going to bother us. And we make sure that we don't operate during that time period. And sometimes that's difficult to schedule, but that's how we address that. My branch supports the implementation of NASA-funded ISS research projects related to fluid physics. And we come on board in the very earliest stages. After NASA's selected a PI, we're usually the first, after NASA's award, headquarters has made that award, we are the first and only contact with the PI during the ground-based development where we're looking at feasibility issues. We help the PIs develop their initial science requirements, which then evolve into engineering requirements, which are handed over to the engineering team to build flight hardware. And we stay with the PI all the way up through cradle to grave sort of thing, up to operation on orbit. We sit on console with the PIs. We support them in data analysis if needed, and revising test matrix and that sort of thing. We do also serve the PI function, but we have to compete, in our branch, we have to compete with the external community to become a PI. Next chart, please. So, fluid physics. Every fall I teach a graduate level transport phenomena class at Cleveland State University, and I spend the first half of the lecture talking about what is fluid physics and what do we mean by transport phenomena. And you get a lot of interesting answers from the students. But in very short, fluid physics is the study of the motions of liquids and gases, and then the associated transport of mass, momentum, and energy. And it's different from other areas of study like thermodynamics where you're looking at end states. We're interested in how we get from one state to the other. These studies arise in nature. I list a few there: meteorology, oceanography, and of course living plants and animals. You heard a lot about that in this morning's talks. And then in technology developments, biological, biochemical, chemical, petroleum, material processing, and then of course the mechanical fluid systems, more traditional. There's been a need for a better understanding of fluid phenomena this has been a field of study for well over 100 years. It's a multidisciplinary research community. We constantly branch off and support other areas such as biology. It's the emergence of these new fields and relevance in both basic is relevant in both basic and applied sciences. And the rest of my talk, I'm going to really talk about the two really key reasons we do research in zero-G. One is to develop technologies for NASA exploration, and the other is for terrestrial and fundamental science reasons. Next chart, please. What's so special about fluid physics and zero-G? Well, I think you heard this morning that, the short answer is you're basically eliminating the conditions that dominate in 1G so that you can start to look at intermolecular forces and other forces that are interacting and study those. What you're essentially eliminating is buoyancy and sedimentation between gas-liquid or liquid-solid phases. And you also have to worry about buoyancy-driven convection in 1G. Go to 0G, that's also eliminated, and that's within a single phase. Next chart, please. Okay, so one of the primary reasons NASA conducts low gravity research is to develop technologies for both robotic and human missions. And the areas that are, and this isn't a complete list, but these are some of the areas that we research that are directly related to fluid physics. We're looking to develop efficient heat transfer systems and these now are typically going to involve phase change, both freeze-thaw systems, phase change material heat exchangers, or boiling and condensation systems. We're also starting to look at life support systems that involve two-phase. Obviously, we have life support systems that function on ISS and have function on other spacecraft, but they're predominantly single-phase systems, and the first evolution of these systems, we needed to be able to test them for months in what we were hoping was relevant conditions. So we worked very hard, the engineers worked very hard to make sure that these were gravity-independent systems, which basically drove you to single phase. The price we paid for that is we have less efficient systems, maybe not quite as reliable, and in some cases, like in chemical reactors, we've actually shown that we can take advantage of microgravity systems and actually operate more efficiently than the same system does in 1G. Other areas, chemical biological reactors, and another big area that we're interested in is a transfer and storage of fluids. NASA's very interested in developing a cryo depot on orbit, and then a transfer of non-cryo fluids as well. And then finally, gas-liquid separation systems. Next chart, please. Okay, so I mentioned the phase change material or freeze-thaw systems. Those are not very gravity dependent, so I didn't really put a chart together for that. But boiling condensation heat transfer systems are highly gravity dependent, and this little blue chart depicts critical heat flux at two different flow levels, and you can see how sensitive it is to orientation in 1G. These heat transfer problems in 0G, you have to consider not only the buoyancy between the two phases, but as I mentioned earlier, the convective buoyancy within a single phase. A couple examples of research that we've been doing. We actually just wrapped up last week a constrained vapor bubble experiment, which is looking at a wickless heat pipe. It was a very successful experiment. We're hoping to launch probably early next year a pool boiling facility, which will have 2 experiments on it, where we'll look at various aspects. We have 2 PIs looking at various aspects of pool boiling. And then in about 5 or 6 years, we just kicked off another experiment that's going to look at flow boiling and condensation. We're actually going to start funding that in next fiscal year. The reason we're so concerned or so interested in this type of heat transfer is that we expect, with the more dense, compact electronics, high energy electronics, we're almost going to be forced to go to this type of a heat transfer, heat removal system. And if we look at nuclear power systems, we're absolutely forced to go to this type of a heat transfer system. Next chart, please. Okay, and then there's gas-liquid phase distribution without heat transfer. I show 2 pictures here, one of flow through a pipe, and the differences in the very top is 2 phases in 1G, and at same flow conditions in 0G. So you see you get a very different distribution of and operation of that system, distribution of phases. These are most commonly found in propulsion and life support systems. And then, of course, the transfer, a very critical area, or technology you want to develop are efficient low-mass systems for transferring liquid from tanks in 0G. We obviously are able to do that. The current systems usually involve vanes and screens, but they're essentially designed to bring fluid in contact with the section that you're going to start removing the fluid, just for the initial drawdown of the fluid. We really don't have any good system or good way to completely draw the tank down without the introduction of artificial gravity. So essentially, the fuel tanks nowadays, we start flowing liquid to the thruster, and then we fire the thruster, we get the artificial gravity, and we can completely drain the tank. Well, obviously, if you're trying to do an on-orbit fuel transfer and you don't have to fire thrusters or any other artificial acceleration, that's a real advantage. Next chart. Okay, multi-phase reactors, both chemical and biological. We're currently working on the development of a fixed bed reactor. We're hoping to fly it in about 3 years. Some of the things that we're interested in are the startups and transient. And this reactor bed will have fixed solid particles and then a gas and liquid phase flowing through it. We're interested in the effects of wetting and non-wetting packing material. We've done aircraft tests that have shown that we clearly get different pressure drops, primarily because of the shift in liquid holdup. Liquid holdup is the final thing we want to look at, and that's very critical because that's you need that to understand the mass transfer, predict the mass transfer, that's very different in zero-G. Next chart, please. Okay, gas-liquid separation devices. We obviously can separate gas-liquid phases in zero-G, but it's through mechanical means, pumps, centrifugal, that sort of thing. What we're looking now is to develop systems that are more passive, that don't require power and or the mass and are more reliable. One particular system that we're hoping to fly in another 3 or 4 years is one that takes advantage of the momentum of the two fluids. And you can see that under the reduced gravity bubble vortex, we can actually swirl the fluid, get the phases to separate or partially separate without adding any additional power. Okay, next chart, please. Okay, so equally important to developing needs for NASA technologies is to use the ISS platform as a test bed for terrestrial applications and fundamental science. And some of the areas, and again, this is not a complete list, include interfacial capillary phenomena, although that overlaps with NASA applications as well, coalescence and aggregation, granular flows, electrostatics of granular materials, colloidal systems, and then other non-Newtonian fluids. Next chart, please. Okay, interfacial and capillary phenomena. We've conducted several experiments in this area over the years. We currently have USPI Mark Weislogo, who's looking at new geometries and trying to develop, he has been developing a more fundamental understanding of capillary effects in these various geometries. He's actually was just flying, is currently flying an experiment now. We also have a joint effort with, we're working with the German Space Agency, DLR, to look at flow through an open channel. And this is really critical in removing a liquid from a tank. If you have an open interface, there's a maximum amount of liquid you can draw through that channel before you get that interface to collapse and you start to ingest bubbles. So that's one of the primary reasons they're hoping to fly their experiment. Next chart, please. Okay, coalescence and aggregation. There's a number of important processes that rely heavily on the coalescence and aggregation of dispersed phases. There's many examples in solids and liquids or liquid drops in gas and so forth. Understanding the mechanisms and controlling them to either enhance or inhibit coalescence is very important. And only in zero-G can you really observe these other forces, and they're primarily intermolecular forces. Next chart, please. Granular mechanics and flows. We had a ISS experiment, was under development until it was a casualty of our budget cuts about 4 or 5 years ago. But this is a very important area. It supports a wide range of industries. Some estimates that industries equal to $1 trillion a year. I list all of them there in that first bullet. But really, there's some fundamental forces that are at play with granular material that you can only observe in zero-G. And we're hoping to get this area of research going again. Next chart. And I think I had a movie in there that's not going to play. Okay, electrostatics of granular materials. This is, think of removing particles, dust particles, filters. We're looking at, preventing dust contamination on spacesuits and other hardware that do extraterrestrial missions. This is also important in laser and printing processes and applying pesticides and herbicides to crops. Next chart, please. Colloids. There's a number of experiments that have flown on both the shuttle and ISS on colloidal systems. And there's many reasons to study these systems. I list a couple here. Matt Lynch, who's a co-I from Procter & Gamble, is currently conducting research with us. He's interested, as an example, in predicting shelf life for soaps and pharmaceuticals and other colloidal fluids that Procter & Gamble are interested in. And he's hoping that, to understand what leads to collapse or the irreversible phase separation of these systems. Anybody's interested in seeing that, send me an email and I can point you to a link where you can see that, and there's actually more information on this. Okay, next chart. Okay, so finally, other non-Newtonian fluids. Just list a couple here. Foams, which is also very important in industry, and MR fluids, which is a class of fluids that where if you apply a magnetic field across them, you change the viscosity, you can get them all the way up to essentially solid-like behavior. And we recently concluded a couple experiments in that field. Next chart, please. Okay, the last 3 or 4 charts I thought I'd throw out. These have bounced around the halls of NASA for 5, 6 years now. There was an NRC report that was released in 2003. It's available to the public, where they were trying to, in this report, they plotted the magnitude of the impact of various high priority areas of research versus the probability of success. So what I did is I highlighted the fluid physics. These are the physical science areas, but the ones I highlighted are very much dependent on understanding fluid physics. And these aren't listed in any particular order, but if you go to the next slide, you'll see the first chart where they basically plot, again, the magnitude of the impact versus the probability of success. And this is for an impact on science and the fundamental knowledge. And what jumps out in the far upper right is where you want to invest your research dollars, because you can get both an impact and you have a high probability of success. So NASA's looking at it, it's like, yeah, we should probably be funding those areas. Well, the key areas in fluid physics are the nucleation or boiling process and multi-phase flow systems. Next chart, please. And this one is the likely impact on terrestrial applications. And in here, what jumps out are, again, multi-phase flow and heat transfer systems and biofluid dynamics, areas in fluid physics that you would want to invest research dollars. And then the third chart, next chart. And finally, this is the impact on NASA technology needs. And what jumps out here for the fluid physicists is multi-phase flow, heat transfer, interfacial processes, and then complex fluid rheologies like liquid crystal displays. And I'll give a little plug for Dave here, because he's going to talk about combustion next. You'll see 9, 10, and 11, which are way up there. Those all have to do with flammability and fire safety. So this particular panel thought that was very critical to NASA to study that. Next chart. And this is my final chart. And I guess, the 2 takeaways that I want to leave you with is, gravity does in fact mask a number of other forces that are at play in many different types of fluid systems. And we have had a number of successful experiments to date. And in fact, this has been a very busy year for us. We got the Fluid Integrator Rack up and running, and we're starting new projects, and we're concluding a lot of projects. So it's been a very exciting, fun year for us. But there's a lot more work to be done. And now that ISS is complete, we really need to do this both in fluids and in all the other areas, both in applied and fundamental areas of study. Any questions? Thank you.